Every image you've ever seen of the solar system has shown it from the same perspective, looking down from above. The sun sits at the center, the planets orbit in neat circles, and everything appears organized and easy to understand. But have you ever stopped to ask yourself a simple question? What does our solar system actually look like from the outside? If you could leave Earth behind, fly past Mars, Jupiter, Saturn, and Neptune, cross the invisible boundary where the sun's influence fades, and continue far enough into the darkness to look back at everything we call home, what would you see? Would the planets still be visible? Would the solar system look like a giant spinning disk, or would it appear as something completely different? The answer is far more surprising than most people realize. Beyond the planets lie enormous hidden structures, vast magnetic bubbles, frozen shells of ancient objects, and even a growing sphere of human-made signals expanding into the galaxy at the speed of light. These structures are so large that they make the planetary system seem tiny by comparison. Today, we're going on a journey beyond the edge of everything familiar, traveling farther than any human has ever gone, to discover what our solar system truly looks like from the perspective of the rest of the universe. And by the end of this journey, you may never look at our place in space the same way again. Every journey beyond the solar system begins with a realization that feels almost impossible to accept: the planets that seem so large and important from Earth become insignificant surprisingly quickly. As we accelerate away from our home world, Earth shrinks into a tiny blue point suspended in darkness. The moon disappears first, then the details of our planet fade until continents, oceans, and clouds are no longer visible. Soon, Earth becomes indistinguishable from countless other points of light. Continuing outward past Mars and the asteroid belt, the inner solar system transforms from a familiar collection of worlds into a distant region surrounding a single bright star. The vast distances between planets, which seem compressed in textbooks and diagrams, reveal their true scale. Space is not crowded, it is overwhelmingly empty. As we move farther from the Sun, the giant planets come into view one by one. Jupiter, the largest world in the solar system, dominates its region with immense size and gravity, yet even Jupiter begins to shrink as distance increases. Saturn's magnificent rings, so breathtaking up close, become impossible to distinguish. Uranus fades into a pale bluish dip, and Neptune, the most distant major planet, marks the edge of what many people imagine to be the solar system. Orbiting nearly 2.8 billion miles, or 4.5 billion kilometers, from the Sun, Neptune receives sunlight that has already traveled for more than 4 hours through space. Yet even this distant giant eventually disappears behind us, becoming another tiny point swallowed by the darkness. Looking back, the entire planetary system that shaped human understanding for centuries has been reduced to almost nothing. Beyond Neptune lies a region that many people have heard about but few truly appreciate: the Kuiper Belt. Unlike the neat planetary orbits shown in diagrams, the Kuiper Belt is a vast ring of icy bodies, dwarf planets, and ancient debris left over from the solar system's formation more than 4.5 billion years ago. Pluto is the most famous resident, but it is only one member of a much larger population. Hundreds of thousands of objects larger than 100 kilometers are believed to exist here, along with countless smaller fragments. Despite these numbers, the Kuiper Belt does not resemble the dense asteroid fields often depicted in science fiction movies. The distances between individual objects are enormous. A spacecraft could travel through the region for years without encountering another object at close range. What defines the Kuiper Belt is not its density, but its scale, a broad, sparsely populated frontier marking the transition between the familiar planetary system and the deeper reaches of space. As we continue outward, another change begins to occur. The sunlight that illuminates the planets grows steadily weaker. At Earth, sunlight is bright enough to support life and fill the sky with daylight. At Jupiter, it is already 25 times weaker. By the time we reach Neptune, it has faded to less than 1,000th of its intensity on Earth. Beyond the Kuiper Belt, the decline becomes even more dramatic. At a distance of 50 astronomical units from the Sun, sunlight is roughly 2,500 times fainter than it is on Earth. The Sun no longer appears as the large, brilliant disk we know from our sky. Instead, it resembles an extraordinarily bright star dominating the darkness. For the first time, a traveler could stare directly toward the Sun without being overwhelmed by its glare. The warmth and brilliance of the inner solar system have been replaced by a cold, silent environment where darkness reigns. This is the moment when our perspective begins to change. From Earth, the solar system feels like a collection of planets orbiting a central star. But from out here, the planets are already gone from sight. Their orbits are invisible. Their individual identities vanish into the vastness of space. What remains is a single bright point of light surrounded by emptiness. The solar system no longer looks like the diagrams found in classrooms and textbooks. It looks like a star alone in the dark. Yet despite how empty it seems, we have not even come close to leaving the Sun's domain. Ahead lies an invisible structure far larger than the planetary system itself, a colossal bubble created by the solar wind, stretching hundreds of astronomical units into space. To truly understand what the solar system looks like from the outside, we must continue beyond the planets and into the hidden boundary where the influence of our star finally begins to fade. After leaving the planets behind and crossing the distant reaches of the Kuiper Belt, it would be tempting to think that we have finally reached the edge of the solar system. The Sun has shrunk into an intensely bright star, the planets have vanished from sight, and the darkness seems endless in every direction. But appearances can be deceiving. Even here, far beyond Neptune, we are still traveling through a vast region dominated by our Sun. Unlike the planets, this region is completely invisible. It cannot be seen with the naked eye, and no photograph can capture its true shape. Yet it is one of the largest structures associated with our solar system. This immense cosmic bubble is known as the Heliosphere, and it extends far beyond anything most people imagine when they think about the Sun's reach. The heliosphere is created by the solar wind, a continuous stream of charged particles flowing outward from the Sun in all directions. Every second, the Sun releases millions of tons of material into space, sending protons and electrons racing through the solar system at speeds of hundreds of miles per second. Near Earth, we experience the effects of this solar wind through phenomena such as auroras and geomagnetic storms. But the solar wind does not stop at Earth, or even at Neptune. It continues outward for billions of miles, carrying the Sun's magnetic field deep into interstellar space. Throughout our journey away from the planets, we have been traveling inside this invisible current without ever noticing it. As we move farther from the Sun, however, the solar wind gradually weakens. The particles spread out across an ever-growing volume of space, losing density and pressure as they travel. Eventually they encounter resistance from something even larger, the interstellar medium. This medium is the thin mixture of gas, dust, and energetic particles that fills the space between stars. Although incredibly sparse by earthly standards, it exerts enough pressure to push back against the outward flow of the solar wind. For billions of years, a constant struggle has taken place at the frontier between these two forces, the Sun's expanding influence and the surrounding galaxy pressing inward. This cosmic battle creates the boundary regions of the heliosphere. The first major transition is known as the termination shock, where the solar wind begins to slow dramatically after traveling faster than the speed of sound in the surrounding plasma. Beyond this region lies the heliosheath, a turbulent zone where solar particles become compressed and chaotic. Here, conditions are unlike anything found near the planets. Magnetic fields twist and interact, particles collide, and the influence of interstellar space becomes increasingly apparent. It is a borderland between two different environments, neither fully belonging to the Sun nor completely to the galaxy beyond. Eventually we reach the most important boundary of all, the heliopause. This is the point where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium. Beyond the heliopause, the Sun no longer dominates the local environment. The particles originating from our star become vastly outnumbered by those arriving from the rest of the Milky Way. Crossing this boundary is, in a very real sense, leaving the Sun's protective bubble and entering true interstellar space. The heliopause is located roughly 120 astronomical units from the Sun, about 4 times farther than Neptune's orbit. It marks the frontier where the solar system's immediate influence gives way to the broader galaxy. Remarkably, humanity has already reached this boundary. In 2012, Voyager 1 became the first spacecraft ever to cross the heliopause. After traveling for more than 3 decades through the outer solar system, it detected a sudden drop in solar particles and a corresponding increase in galactic cosmic rays. The data revealed that it had entered interstellar space. Voyager 2 followed in 2018, confirming the existence of this boundary through similar measurements. These 2 spacecraft remain the only human-made objects to have crossed the edge of the heliosphere. Even now, they continue their silent journey into the darkness, carrying with them messages from Earth and expanding humanity's reach farther than ever before. From a great distance, the heliosphere itself would not appear as a perfect sphere. The solar system is moving through the Milky Way at roughly 43,000 miles per hour, and this motion shapes the heliosphere much like the movement of a boat shapes the water around it. The leading edge becomes compressed as it pushes into the interstellar medium, while the trailing side stretches outward into a long tail known as the heliotail. Some models suggest this tail may extend for hundreds or even thousands of astronomical units behind the solar system. Rather than a simple bubble, the heliosphere resembles a gigantic cosmic comet, with the Sun embedded near its front and an invisible wake stretching behind it through the galaxy. If an advanced civilization could somehow detect charged particles and magnetic fields from afar, this heliosphere would be one of the defining features of our solar system. It would reveal that our star is actively interacting with the surrounding galaxy, carving out a protective cavity in interstellar space. Yet to ordinary eyes, the entire structure would remain completely invisible. No glowing boundary marks its edge. No brilliant shell outlines its shape. A traveler crossing the heliopause would see nothing unusual at all. The change exists only in the physics of the environment, the particles, the radiation, and the magnetic fields that surround them. By crossing the heliopause, we have left behind the Sun's protective bubble and entered the vast ocean between the stars. Yet even now, our journey is far from over. Most people would assume that interstellar space marks the end of the solar system, but that assumption is wrong. Beyond this invisible boundary lies something far larger than the heliosphere itself, a colossal shell of frozen objects extending nearly a light year from the Sun, hidden in the darkness, rarely discussed, and never directly observed. It represents the true outer frontier of our solar system. To find it, we must continue deeper into the void, toward the mysterious realm known as the Oort Cloud. Crossing the heliopause feels like the end of a journey. After all, we have left the Sun's protective bubble and entered interstellar space. The solar wind no longer dominates our surroundings, and the familiar influence of our star seems to have faded into the distance. To most people, this would appear to be the true edge of the solar system. But the reality is far more astonishing. Even after traveling beyond the heliosphere, we are still deep inside the Sun's domain. The solar system does not end where the solar wind ends. In fact, one of its largest and most mysterious structures still lies ahead, a structure so vast that it completely changes our understanding of what the solar system really is. Far beyond the heliopause exists a region known as the Oort Cloud. Unlike the flat disk formed by the planets and the Kuiper Belt, the Oort Cloud surrounds the solar system in every direction. It is not a ring. It is not a plane. It is a gigantic three-dimensional sphere of icy objects completely enclosing everything inside it. If the planets make up the visible architecture of the solar system, then the Oort Cloud is its hidden outer shell. It stretches above and below the planetary plane, extending into the darkness in all directions. From a distance, it represents the true shape of the solar system far better than any textbook diagram ever could. The origins of the Oort Cloud reach back more than 4.5 billion years to the chaotic birth of the solar system. During that time, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were still forming and migrating through a crowded disk of gas, dust, and debris. Their immense gravity acted like cosmic slingshots, flinging countless smaller objects outward. Some of these bodies gained enough speed to escape the Sun entirely, disappearing into interstellar space forever. Others were launched into enormous orbits that carried them far beyond the planets but not quite beyond the Sun's gravitational reach. Over hundreds of millions of years, interactions with passing stars and the tidal forces of the Milky Way gradually reshaped these elongated orbits into a vast spherical distribution. The result was the Oort Cloud, a frozen reservoir containing the leftover building blocks of planetary formation. The scale of this structure is almost impossible to comprehend. The heliopause sits roughly 120 astronomical units from the Sun, already far beyond the orbit of Neptune. But the Oort Cloud may begin around 2,000 astronomical units away and extend as far as 100,000 astronomical units from the Sun. At its outermost edge, it reaches nearly 1 light-year into space. To put that into perspective, the nearest star system, Alpha Centauri, is only about 4 light-years away. This means the edge of our solar system may extend nearly 1/4 of the distance to the nearest star. Suddenly, the planets that seemed so important at the beginning of our journey occupy only a tiny central region within an enormously larger structure. Despite its immense size, the Oort Cloud remains one of the most elusive features of the solar system. No spacecraft has ever reached it. No telescope has directly observed it. Every illustration of the Oort Cloud is based on scientific models rather than actual photographs. Yet astronomers are confident that it exists because of the evidence it leaves behind. That evidence arrives in the form of long-period comets, ancient icy bodies that occasionally appear in the inner solar system from seemingly random directions. Unlike objects originating in the Kuiper Belt, these comets do not follow paths aligned with the planetary plane. They can approach from above, below, or virtually any angle in the sky. Their distribution reveals the existence of a spherical source surrounding the solar system, exactly what astronomers would expect if the Oort Cloud were real. Imagine one of these frozen objects drifting in the darkness near the edge of the Oort Cloud. For billions of years, it circles the Sun at unimaginable distances. There is no daylight, no warmth, and no visible motion except the slow movement of distant stars. Then, perhaps a nearby star passes through the region, or the gravitational pull of the Milky Way subtly alters its orbit. The object begins a long inward fall toward the Sun. The journey may take hundreds of thousands or even millions of years. Gradually, sunlight grows brighter. Frozen gases trapped within the comet begin to evaporate. A glowing cloud of gas forms around it, followed by a brilliant tail stretching millions of miles through space. For the first time since the solar system was young, this ancient traveler becomes visible. What appears to us as a spectacular comet is actually a messenger from the very edge of the Sun's realm. Comets such as Hale-Bopp and Hyakutake are examples of these distant visitors. For a brief moment in cosmic time, they illuminate our skies and capture our attention. Yet their true significance lies in where they came from. Each one is evidence of a hidden population of icy bodies orbiting at the farthest reaches of the solar system. Without them, we might never have known the Oort Cloud existed at all. They are clues scattered across the darkness, pointing toward a structure too distant and too faint to observe directly. What makes the Oort Cloud especially fascinating is that it changes the way we think about the solar system's shape. Most people imagine the solar system as a flat disk because that is where the planets reside. But the planets represent only a tiny fraction of the Sun's gravitational domain. Viewed on the largest scales, the solar system is not disk-shaped, it is nearly spherical. The Oort Cloud surrounds everything, creating a frozen shell that extends far beyond the planetary system. If an observer from another star system could somehow map the Sun's gravitational influence, they would find a giant sphere rather than a flat arrangement of planets. And yet, despite its enormous size, the Oort Cloud would remain almost completely invisible. The objects within it are separated by vast distances, and each one reflects only a tiny amount of sunlight. An alien astronomer looking toward our solar system would not see a glowing shell or a dense cloud. They would see nothing at all. The largest structure associated with our solar system is effectively hidden from view. Its existence can only be inferred through the occasional comet that escapes its frozen depths and journeys inward toward the Sun. As we continue moving away from the Oort Cloud, the scale of everything we have traveled through becomes clear. The planets are now unimaginably distant. The heliosphere has vanished behind us. Even the immense sphere of the Oort Cloud begins to shrink into the darkness. For the first time, we are approaching a distance where the entire solar system can be viewed as a single object. What will remain visible? Not the planets. Not the comets. Not the invisible shell of ice surrounding the Sun. From here, nearly everything disappears. The only thing left is a single star shining against the backdrop of the Milky Way, a star that, from afar, looks surprisingly ordinary. In the next stage of our journey, we will discover what the solar system truly looks like from the perspective of another star. At last, we have traveled beyond the outer reaches of the Oort Cloud. The vast shell of frozen objects that once surrounded us has faded into the darkness, and for the first time in our journey, the entire solar system lies behind us. We are now several light-years away, drifting through the space between stars. Looking back toward home, a remarkable realization emerges. Everything humanity has ever known, the Sun, the planets, the moons, the asteroids, the comets, every mountain, every ocean, every city, every person who has ever lived, has become almost impossible to see. The grand structure that seemed so enormous from within has shrunk into something astonishingly simple, a single point of light. From a distance of 10 light-years, the Sun no longer dominates the sky. It appears as just another star among thousands. It shines with a warm yellow-white color, characteristic of a G-type main sequence star, but there is nothing visually extraordinary about it. In fact, if you were standing on a planet orbiting another nearby star and looking at our Sun, you might never notice it at all. It would not be the brightest object in your night sky. It would not stand out from the countless stars scattered across the Milky Way. To an outside observer, the Sun would appear ordinary, a middle-aged star of average size and brightness quietly burning in a remote corner of the galaxy. This perspective is difficult to accept because from Earth, the Sun feels overwhelmingly important. It is the source of all life, the center of our planetary system, and the dominant object in our sky. Yet in the broader context of the universe, the Sun is just one star among hundreds of billions. Many stars are larger, hotter, brighter, and more massive. Some shine thousands or even millions of times more intensely. Others exist in spectacular binary systems or are surrounded by brilliant nebulae. Compared to these cosmic giants, our Sun is modest. It is neither rare nor exceptional. It belongs to a category of stars so common that astronomers have identified countless similar examples throughout the galaxy. But what about the planets? Surely Jupiter, the giant of our solar system, would be visible from this distance. After all, Jupiter is enormous, more than 11 times Earth's diameter and more massive than all the other planets combined. Yet even Jupiter vanishes into invisibility. The same is true for Saturn, Uranus, Neptune, and Earth itself. The planets are simply too small and too faint compared to the overwhelming brightness of the Sun. Their reflected light is drowned out by the star they orbit. To an observer several light-years away, the planets disappear completely. This raises an interesting question. If the planets cannot be seen directly, how would another civilization know they exist? The answer lies in gravity. Every planet exerts a gravitational pull on the Sun, causing the star to move slightly as the planets orbit around it. Instead of remaining perfectly still, the Sun performs a tiny wobble around the solar system's center of mass. Jupiter is responsible for most of this motion because of its immense mass. Over the course of its orbit, it pulls the Sun back and forth in a predictable pattern. To an astronomer equipped with sensitive instruments, this wobble could reveal the presence of planets even when the planets themselves remain invisible. This is precisely how many exoplanets have been discovered. Astronomers often cannot see distant planets directly. Instead, they study the stars those planets orbit. By measuring tiny shifts in a star's motion or small dips in its brightness when a planet passes in front of it, scientists can infer the existence of entire planetary systems. In fact, if an advanced civilization were observing our Sun from a nearby star system, they might detect Jupiter first. After years of careful measurements, they could identify Saturn, and perhaps even Neptune. Detecting Earth would be far more difficult, but not impossible with sufficiently advanced technology. Some civilizations might go even further. Instead of merely detecting the planets, they could analyze the light coming from Earth itself. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching distant observers. By studying this filtered light, scientists can identify the chemical composition of the atmosphere. Oxygen, methane, carbon dioxide, and water vapor all leave recognizable fingerprints. If a civilization possessed instruments far more advanced than ours, they might discover that one of the Sun's planets has an atmosphere rich in oxygen and traces of biological activity. Long before they ever saw Earth directly, they could suspect that life exists here. Yet visually, the solar system remains underwhelming. The heliosphere is invisible. The Oort cloud is invisible. The planets cannot be seen. Even the Kuiper Belt has vanished into darkness. From several light-years away, all the complexity of our cosmic neighborhood collapses into a single star. The enormous structures we spent our journey exploring are hidden from view. To the rest of the galaxy, our solar system does not appear as a collection of worlds. It appears as a tiny point of yellow light suspended among countless others. And yet there is one thing that makes our solar system different from many of the stars surrounding it. One thing that extends beyond the planets, beyond the heliosphere, and beyond even the distant Oort cloud. Unlike gravity or reflected sunlight, it travels outward at the fastest speed the universe allows. It has already crossed dozens of light-years and continues expanding every second. It is not a natural phenomenon created by the Sun. It is something humanity created without intending to. And it may be the most visible sign of our existence to the wider galaxy. In the next chapter, we will explore the only part of our civilization that has truly escaped the solar system, the growing sphere of radio signals known as the radio bubble. From a distance of several light-years, our solar system appears almost completely invisible. The planets cannot be seen. The Oort cloud is hidden in darkness. Even the vast heliosphere leaves no visible trace against the backdrop of the Milky Way. To any distant observer, the Sun looks like an ordinary yellow star surrounded by secrets they cannot directly observe. Yet there is one feature of our solar system that does not depend on reflected sunlight, gravitational measurements, or advanced telescopes. It is something humanity created unintentionally, something that has already traveled farther than any spacecraft we have ever launched. It is a signal, and it has been expanding into the galaxy for more than a century. The story begins in the early 20th century, when humans first learned how to broadcast radio waves across great distances. At the time, nobody was thinking about interstellar communication. Engineers and inventors were simply trying to send messages across cities, countries, and oceans. The first radio broadcasts carried music, news reports, military communications, and experimental transmissions. Later came television signals, radar systems, satellite communications, and countless other forms of electromagnetic radiation. Every one of those signals traveled outward from Earth at the speed of light. Most were intended for receivers on our planet, but the laws of physics do not care about human intentions. Any signal that escapes Earth's atmosphere continues moving into space forever. As the decades passed, those transmissions accumulated into something extraordinary. Around our solar system, an expanding sphere of radio waves began to grow. Astronomers sometimes refer to this as the radio bubble, a shell of artificial electromagnetic radiation spreading outward in all directions at approximately 186,000 miles per second, or 300,000 kilometers per second. The earliest broadcasts from the 1920s are now more than 100 light-years away from Earth. Every year, the bubble expands by another light-year, carrying with it an ever-growing record of human civilization. Imagine what exists within that expanding sphere. It contains the voices of early radio announcers. It contains the first live news broadcasts. It contains historic speeches, wartime communications, scientific experiments, television programs, sporting events, and countless personal conversations transmitted through radio systems. Every generation has added new layers to the signal. Long before any human traveled into space, a version of humanity had already begun spreading through the galaxy in the form of electromagnetic waves. From nearby star systems, these signals would be extraordinarily faint. Radio waves become weaker as they spread outward, dispersing their energy over an ever larger area. This effect, known as the inverse square law, causes signal strength to decrease dramatically with distance. By the time Earth's earliest broadcasts have traveled dozens of light-years, they are buried beneath cosmic background noise and natural radio emissions from stars and galaxies. Detecting them would require technology far beyond what humanity currently possesses. Nevertheless, the signals remain there, expanding relentlessly into the darkness. For a sufficiently advanced civilization, the radio bubble could serve as evidence that intelligent life exists around our sun. Unlike the subtle gravitational wobble caused by planets, radio transmissions contain patterns. They carry information. Natural phenomena produce radio waves, but they do not create structured broadcasts, encoded messages, or complex signals containing language, music, and technology. If an advanced civilization intercepted and decoded even a fraction of our transmissions, they would immediately recognize that the source was technological rather than natural. What would they learn about us? Perhaps they would discover fragments of our history. They might detect evidence of our scientific achievements and our cultural diversity. They might hear voices speaking hundreds of different languages. They might observe the rise of modern technology through changes in our communications. They could even witness our conflicts, our triumphs, and our mistakes. In a sense, the radio bubble acts as a time capsule, preserving snapshots of humanity as it existed at different moments throughout the past century. Yet there is an important limitation. The farther away a civilization is, the older the information they receive. An observer 50 light-years from Earth is currently receiving signals that left our planet 50 years ago. Someone 100 light-years away is only now encountering broadcasts from the early 20th century. Across the galaxy, different regions of space contain different chapters of our story. No one sees the present-day Earth unless they are close enough for today's signals to have already reached them. The idea of the radio bubble naturally raises one of humanity's oldest questions: is anyone listening? At present, we have no answer. The Milky Way contains hundreds of billions of stars and potentially billions of planets capable of supporting life. Yet despite decades of searching, we have found no confirmed evidence of extraterrestrial civilizations. It is possible that intelligent life is rare. It is possible that civilizations are common but separated by immense distances. It is also possible that our signals are simply too weak to be noticed. The universe has remained silent so far, but silence does not necessarily mean emptiness. Ironically, the most famous human attempt to communicate with extraterrestrial life is not the radio bubble at all. In 1977, NASA launched the Voyager spacecraft carrying the Golden Record, a collection of sounds, images, and messages representing life on Earth. The record was designed as a greeting to any civilization that might someday encounter the spacecraft. Yet even Voyager 1, the fastest human-made object ever launched, would require tens of thousands of years to reach the nearest stars. By comparison, our radio transmissions have already traveled more than 100 light-years. Long before Voyager arrives anywhere, the radio bubble will have crossed hundreds more star systems. This means that humanity's first introduction to the galaxy was not intentional. We did not carefully craft a message before announcing our presence. We simply began communicating with each other, and the universe overheard. The radio bubble is the accidental consequence of technological civilization. It is the only part of humanity that has truly escaped the solar system on a meaningful scale. While spacecraft crawl slowly through interstellar space, our electromagnetic footprint races ahead at the speed of light, expanding year after year without pause. And so, from the perspective of the wider galaxy, our solar system is defined by two things. First, there is an ordinary yellow star shining among billions of others. Second, there is a faint but growing sphere of artificial signal surrounding it. The star alone would attract little attention. But the signals tell a different story. They suggest that somewhere around that unremarkable star, a species has learned to communicate, to build technology, and to leave traces of its existence beyond its home world. Whether those traces will ever be discovered remains one of the greatest unanswered questions in science. Perhaps no one is close enough to hear them. Perhaps countless civilizations have already detected them and chosen not to respond. Or perhaps, somewhere in the darkness, another young civilization is broadcasting its own signals into space, wondering if anyone is listening. As our journey reaches its end, one truth becomes clear. From the outside, the solar system is not defined by its planets, its comets, or even its immense invisible boundaries. It is defined by a single star and a growing echo of intelligence spreading outward through the galaxy. That echo is humanity's voice, traveling through the darkness long after it has left its source behind. And even now, at this very moment, it continues its endless journey into the unknown.